Okay. Oh, there it is again. I started with okay and I didn't want to start with okay. Anyways, 5.6 integration by U-substitution. Now, this is a technique that is going to allow us to start to explore other types of problems. If you look back in your notes, all right, and you look back in all the videos, we've always used three rules. We use the power rule, we use the exponential rule, and we use the log rule. Okay, and those rules respectively are the integral of x to the n dx equals 1 over n plus 1 x to the n plus 1 plus c, that's our power rule. The exponential rule, e to the ax dx is going to equal 1 over a e to the ax plus c. Okay, that's our exponential rule. And then the last rule is that log rule, which was 1 over x dx is going to equal the natural log of the absolute value of x plus c. Okay? Now the question becomes this. What if one of these three rules don't apply? All right? Now, how are you going to know that? Well, I'm going to show you, okay? So, a long time ago, when we looked at a problem like this, when we wanted to find a derivative of something like x squared plus 1 cubed times 2x, all right, we had two options. Option 1 was to multiply everything out. That was option 1, multiply everything out, okay? All right, and that wasn't a bad option. But unfortunately, what if that exponent was not a 3? What if it was a 10? You're trying to tell me you would want to sit there and multiply x squared plus 1 times itself 10 times. All right? So then we learned option 2. All right? Option 2 dealt with the product rule. Okay? Now option 2, the product rule, said, well, if you had two different functions being multiplied, okay, you could go ahead and label one f, one g, and then find a derivative that way. All right? So the first thing that I kind of want you to recognize, all right, is that sometimes if I wanted to say, let's do a problem like this, notice what I did. Okay, notice what I did is I just put the integral and a dx on the end, all right? Notice here you have the product of two things being multiplied, all right? Even more importantly, this is what I want to do here. Notice that if you were to take the chain rule, all right? In other words, if you wanted to differentiate x squared plus 1 cubed, you notice you would get 3 times x squared plus 1 all raised to the second power times the derivative of the inside, which would be 2x. All right? What I'm really focused on here is this. I know on the inside of the cubed function, the x squared plus 1, notice I have the derivative of that outside. All right? When you start to recognize that and you're integrating, you can apply a rule called U-Substitution. Okay? Because right now you have two options. You have two options to integrate this problem. Option 1, multiply everything out. Okay? And then apply your power rule. All right? Or option 2, U-Substitution. So let me show you how U-Substitution works, okay? Let me show you how this works. So as soon as you notice that the integral of x squared plus 1 cubed times 2x times dx, once you recognize that, oh my God, I actually have a chain rule in there, okay? What you're going to do is you're going to let u equal the inside function of the chain. So you're going to let it equal x squared plus 1. You're going to let it equal this right here. Okay? And then you're going to find what we call the differential. All right, now we've studied differentials in the past. Remember chapter 3? We dealt with those differentials. So you're going to take the derivative of u, which is going to equal 2 times x dx. Okay? So it's the differential. All right? Now, this is my little thing, okay? I think every professor prefers one or the other. This is my thing. If you ever have a constant right here, if you ever have a coefficient out front, what I want you to do is I want you to take this whole thing, okay? And I want you to rewrite it as u equals x squared plus 1. And then I want you to divide both sides by 2 to give us 1/2 du equals x times dx. Okay? Now, there is a reason why I want you to do that. So, first thing I wanted to do is show you how to apply U-substitution, which is exactly what I just did. Now what I want to do is I'm going to rewrite the problem and I'm going to make the appropriate substitutions, and I want to see you where all this is coming into play. So, let me get out my black marker here. So I'm going to rewrite the problem. The integral of x squared plus 1 cubed times 2x dx. All right? I notice right here I have a 2, and since everything's being multiplied, I'm allowed to pull that out front. So that's going to give me 2 times the integral of x squared plus 1 cubed x dx. Okay? Now, I see that I have a chain rule. All right, I see that I have a chain rule. So I use U-substitution, and here is what you got to do. And this, if you've done it correctly, all right, this will always happen. First, wherever you see, let me write the word U-sub. Wherever you see x squared plus 1, you know what? Let me use a highlighter. Wherever you see x squared plus 1, you are going to replace that with the letter u. Okay? And wherever you see, oh, that doesn't show up nicely at all. Wherever you see x times dx, you're going to replace that with 1/2 du. So my problem turns out to be, and I'm going to write in red, u to the third power times 1/2 du. Now, real quick, I'm going to pull the 1/2 out front, which means I'm going to take 2 times 1/2, or 2 over 2, times the integral of u to the third du. So, if you look directly above, all right, you ask me, what problem seems a little bit easier to integrate? This, which you would have to multiply everything out, distribute the 2x, gather all your like terms, and then apply the power rule. Or, if you can recognize that you have this chain rule that is staring you in the face, if you can see that, then you can apply U-substitution, which is very simple to do, and you rewrite your problem in terms of the letter u. Now all we have to do, well, we know 2 over 2 is 1, and the integral of u to the third is going to be 1/4 u to the 4 plus c. And then our last step is to make that substitution again. Because remember, I gave you the problem in x's, so I want an answer in x. Just like if I paid you for something and I paid you dollars, U.S. currency, I would expect U.S. currency back. So this is going to be 1/4 times, well, u equaled x squared plus 1. So it's going to be 1/4 times x squared plus 1 raised to the 4th plus c. Okay? And there's our first example of U-substitution. Now I'm going to do another one, obviously. Okay? So let's go ahead. Let's look at the next example. So with this example, the problem is going to get a little bit more difficult. E to the x cubed times 2x. Nope. Let's try this again, Mr. Float. The integral of e to the x cubed times x squared dx. Okay? So, once again, if you look, I have this x cubed right here. Notice the derivative of x cubed is 3x squared, right? Or just x squared. Remember, with constants and integration, you pull them out front. So the thing is, and like I said, you got to get used to just seeing this, okay? You got to get used to seeing this, all right? So I'm going to let u equal x cubed du is going to equal 3x squared dx. In other words, I'm taking the derivative of u, okay? Now, I have a constant, or a coefficient, I'm sorry, so I'm going to divide both sides by 3. So that's going to give me u equals x cubed for the first, and the second is going to be 1/3 du equals x squared dx. And like I said, you will always, always, always be able to match this up, okay? So here's my x third. There's my x to the third. And here is my x squared dx. And there's my x squared dx. So I'm going to go ahead and rewrite my problem as the integral of e to the u times 1/3 du. I'm going to take the 1/3 and pull it out front to give me e to the u du. I know the integral of e to the u is e to the u plus c. And then the last thing I'm going to do here, is I'm going to make my U-substitution to write 1/3 e to the x cubed plus c. And there's your answer right there for that problem. So the more and more you actually do this, okay, the easier and easier this gets. All right? U-substitution allows us to take what looks like chain rules and allows us to integrate them very quickly. Okay? Let's try another example here. How about this? How about the integral of x to the fourth minus 12, all raised to the negative 1, times x cubed dx. Okay? So hopefully now you're starting to see right here, you have x to the fourth minus 12, and you know the derivative of x to the fourth is 4x cubed. So that's basically right there. You're missing the 4, but that's okay. So let's let u equal x to the fourth minus 12. Okay, the inside function of this chain rule. All right. Du is going to equal 4x cubed dx. Now let's rewrite it, because what I'm going to do is divide both sides by that coefficient. So u equals x to the fourth minus 12. 1/4 du equals x cubed dx. Now, let's just make sure, let's match everything up so we know we're allowed to use U-substitution. So there's x to the fourth minus 12, and there's x to the fourth minus 12, which is the inside function only. You don't worry about the negative 1, because that would be the outside function if we were to apply the chain rule. Now, x cubed dx, x cubed dx. So because everything matches up, I'm going to rewrite this as the integral of u to the negative 1 times 1/4 du. All right? Now, I'm going to take the 1/4 out front. And we know that u to the negative 1 is really 1 over u du. And what's the integral of 1 over u? Well, that's going to be 1/4 times the natural log of the absolute value of u plus c. And then I'm going to make my substitution again. Get my answer back in the letter x. 1/4 natural log u is x to the fourth minus 12. So it's 1/4 times the natural log of the absolute value of x to the fourth minus 12 plus c. Okay? All right, let's see how many more examples I have here. One more. All right, one more example. Perfect. Now, Just because we're using U-substitution doesn't mean that this only applies to indefinite integrals. Let's look at a definite integral, all right? So example, let's evaluate the integral from 4 to 5 of dx over 3 minus x, okay? Now, I know this may look a little weird at first, but what I'm going to do is I'm going to rewrite this first because I want you to see it. Just because that dx is in the numerator, what I'm going to do is rewrite it as 1 over 3 minus x dx. Sometimes when you put the dx in the numerator, it confuses students. So normally we see it off to the right-hand side, so I'm going to still do that for us, okay? Now here, notice it's 1 over 3 minus x. We don't have a rule for something like that, okay? We have a rule for 1 over x, but not 1 over like a binomial. In other words, two things being added or subtracted in that denominator. So what we're going to do is we're going to try it. We're going to let u equal 3 minus x, okay? So the derivative of u is going to equal negative 1 times dx. And remember, I have that coefficient, so I'm going to divide both sides by negative 1. So u is going to equal 3 minus x, and negative du is going to equal dx. Well, let's see if everything matches up then. So 3 minus x, 3 minus x. So far, so good. Dx, dx, perfect. So everything matches up. So let's go ahead and let's rewrite. I got the integral of 1 over u du. Now, I want you to see right here and right here, okay? Notice I did not put in my upper or lower limits. You don't have to do that. I'm going to do this problem two different ways. The first way, I'm going to keep it consistent with the way that we've been doing it the whole time, all right? Now, the reason why I didn't put anything for the upper or lower limits, okay? The reason why, so let me write this out. The reason for no upper / lower limits is we converted from the variable x to the variable u. We made that substitution. So 4 and 5 are no longer valid entries for the letter u. They only work for x. So if you want to keep it that way, that is fine by me. All right. So from here, what we would do is we would evaluate the integral of 1 over u du, which is going to be the natural log of the absolute value of u. Now, this is a definite integral, so I'm not going to include the plus c. But what I am going to do is I'm going to rewrite this in terms of x because that's what our variable was. Okay? So that's going to give me the ln. Now, remember, we let u equal 3 minus x, so this is going to be the ln of 3 minus x. It's the absolute value of 3 minus x. Now I can evaluate this between 4 and 5. Okay? So if I evaluate this between 4 and 5, I get the natural log of the absolute value of 3 minus 5 minus the natural log of the absolute value of 3 minus 4, which is going to be the natural log of the absolute value of negative 2 minus the natural log of the absolute value of negative 1. So I got to do the absolute value first. So it's going to be the ln of 2 minus the ln of 1, which is nothing more than just the natural log of 2, because the natural log of 1 goes to 0. Okay? Oh. I made a mistake all the way at the beginning. Here's my mistake. I'm going to throw it in there real fast. I forgot. du equaled negative 1. So there's a negative here, a negative here, a negative here, which, sorry about this, which means negative, negative, negative. So my answer is negative ln of 2. All right? Really sorry about that negative mistake, but, I think you could figure it out from there. All right? Now, that was the first way to do this problem. In blue is going to be the second way. All right, so give me a second here. I'm going to catch up. So we went ahead and we made negative. Don't want to forget that negative this time. So it's going to be negative 1 over u du, okay? All right, now, remember, we let u equal 3 minus x, and we let du equal negative dx, where we rewrote it as u equals 3 minus x, and negative du equal dx, okay? So now we're all caught up. Now, the last thing we spoke about up here was the fact that I did not include the upper and lower limits because we converted from the variable x to the variable u. Now, if you wanted to, once you converted into the letter u, you could take your limits. So we can take the upper and lower limits and convert them into terms of u, okay? In other words, we know that u equals 3 minus x. So, my upper limit, I can rewrite that as u equals 3 minus 5, which is negative 2, okay? And then my lower limit, well, I can convert that, u equals 3 minus 4, which is negative 1. So now these two variables, or I'm sorry, did I say variables? These two constants are valid for u. So what I can do is rewrite my problem as negative integral from negative 1 to negative 2 of 1 over u du, which is going to equal negative ln of the absolute value of u from negative 1 to negative 2. You do not have to convert back to x here if you don't want to. What you have to remember is you got to convert the limits. So limits must be converted if you want to stay in the variable of u, okay? So notice here, I'm going to get the negative ln of the absolute value of negative 2 minus the natural log of negative 1, okay? Let me put this in brackets because the negative it will be distributed for both of them, okay? Let me try to write that nicer. There we go. This is going to give me the negative ln of 2 and then plus 0 because I know that is going to go to 0, or just the negative natural log of 2. So you still get the same exact answer. The question becomes, do you want to stay in u's or do you want to convert back into x's? Doesn't matter to me. It only matters to you. Okay? So that's it for chapter 6. Or no, I'm sorry, chapter 5. I'm going to start working on lectures for chapter 6 over the weekend, and they'll be up by hopefully early next week. So I hope you enjoyed the video, and I will see you in the next one. Bye-bye.